Okay, so welcome to the final section of 6.2. I want to note something. So when evaluating an expression, involving an inverse trigonometric function, we usually let or set it equal to, let me write it that way, set it equal to theta for ease of calculation. Ease of calculation. Okay, so what does this mean? Let me show you. So for example, let's evaluate the following. So number one, let's say I have inverse sine of tangent of pi over 4. Actually, let me make that a bracket on the other side. Okay, so I have inverse sine of tangent of pi over 4. What I'd like to do is I'd like to call this inverse sine. Let's call it theta. So what do I get? I get that theta is equal to inverse sine of, well, what is tangent of pi over 4? Well, both sine and cosine are the same, so it's 1. So now when I rewrite, you'll notice what happens. If I use theta, I get that 1 is equal to regular sine of theta, and this makes a lot more sense than using y. So now I can ask myself, so at what angle theta is sine equal to 1? Well, I know that sine is invertible between negative pi over 2 and pi over 2 inclusive, so this is at 90 degrees. So that's the answer. Okay, so let's do another one. So number 2, let's say I have cosecant of sine inverse, or inverse sine, of 1/2. So now we have that cosecant is on the outside. So what I'm going to do is I'm going to focus on the inside, and I'm just going to let theta be equal to, let's do inverse sine of 1/2, because that's equivalent to saying 1/2 is equal to sine, regular sine of theta. Okay, well that means that the angle theta must be pi over 6, because that's the allowable region. So therefore, if I have cosecant of sine inverse of 1/2, I can now replace sine inverse of 1/2 with what I found it to be. I found it to be pi over 6. Okay, well what is cosecant of pi over 6? It's the reciprocal to sine of pi over 6. So I should get 2. Okay, let's do another one for good measure, shall we? Let's see. Do I have enough room? Maybe I should move down to the next page. So number 3. Let's say we have tangent of arc sine of root 2 over 2. Okay, so once again, I'm going to focus on the inverse. So I'm going to let theta be inverse sine, because that's what arc means, of root 2 over 2. So that is equivalent to saying root 2 over 2 is equal to regular sine of theta. Okay. Well, that must mean that theta is pi over 4. Okay, so now let's go back to the beginning. So we have the tangent of sine inverse, or arc, of root 2 over 2 can now be rewritten as tangent of, what did I find that was? It was simply pi over 4. Tangent of pi over 4 is 1, and there we are. Okay, so let's recall before I go on to the next 3 problems. So let's recall. That cosine squared theta plus sine squared theta is equal to 1. That's my main Pythagorean identity. So of course the next one, dividing by cosine squared, would be 1 plus tangent squared theta is equal to secant squared theta. So I believe I can move this up and save myself some room. Or I could divide the first equation through by sine squared to get cotangent squared theta plus 1 is equal to cosecant squared theta. These are the main Pythagorean identities. Okay, so for example, how am I going to use these? So let's express cosecant, oh that's terrible, cosecant of inverse sine of x as an algebraic expression, in x. Okay, so we have cosecant of inverse sine of x. Okay, so what I always want to do is I always want to focus on the inverse function, and I let my angle theta always be equal to the inverse function. So let's let theta be equal to sine inverse of x. And the reasoning behind this is I can isolate x is regular sine of theta. Okay, and you might think, okay, how is that going to help me? Well, do you agree that 1 over x, how shall I say this, that if I flip this upside down on both sides, the reciprocal to sine is cosecant of theta. Agreed? Okay, now let's go back to the beginning. So I was given cosecant of inverse sine inverse of x, but what did I let sine inverse of x be equal to? I let it be equal to theta, so I can write this as cosecant of theta. And I just found that cosecant of theta was 1 over x, so there we are. Cosecant of sine inverse of x is 1 over x. Kind of makes sense, since cosecant is a reciprocal. Okay, let's do another one. So for example, express, let's do tangent of secant inverse of x as an algebraic expression in x. Algebraic, meaning without any trig parts, algebraic expression in x. Okay, so I will start with, I'll keep the color code the same, so tangent of inverse secant of x. So of course, I always let theta be the inverse function, secant inverse of x, so that I can translate this into x is equal to normal secant of theta. Okay, so now I need to somehow to go from secant to tangent, but I do have my Pythagorean identities, right? I know that 1 plus tangent squared theta is secant squared theta. So let's use that. So semicolon. 1 plus tangent squared theta is equal to secant squared theta. And I'd like to solve for tangent. So I claim that tangent squared theta is equal to secant squared theta minus 1, or tangent of theta is the square root of secant squared theta minus 1. Okay, so how's that going to help me out? Well, what do I have? I have tangent of secant inverse of x, right? But do you agree that secant inverse of x was theta? So I can write this as tangent of theta. Okay, well, according to what I have over here on the right, tangent of theta is the square root of secant squared theta minus 1. And I know that secant of theta is x. So I can write this as x squared minus 1, and there we are. Now I have tangent of secant inverse of x as an expression without trig functions and solely in x. Okay, let's do another one. One more for good measure. So for example, let's express cosine of sine inverse of x as an algebraic expression. Algebraic expression in x. Okay, same color code. Let's do cosine of inverse sine of x. Of course, I'm going to let theta be the inverse trig function. So let's let theta be equal to inverse sine of x, so that I can rewrite this normally as x is normal sine of theta. So once again, I need to somehow go from sine of theta to cosine. So I note my main Pythagorean identity, semicolon, cosine squared theta plus sine squared theta is equal to 1, which means that cosine squared theta is 1 minus sine squared theta, which means that cosine of theta is the square root of 1 minus sine squared theta. Okay, so let's go back to the top. I have cosine of inverse sine of x, but inverse sine of x I called theta. So this is really cosine of theta. Well, cosine of theta is the square root of 1 minus sine squared of theta. Okay, but sine of theta is x, so I can rewrite this as the square root of 1 minus x squared. And now I have no trig functions, and this is an algebraic expression solely in x.